Today we're starting in your workbooks on page 489. This is Module 9. Module 9 is all about exponential functions, and that's exactly what today's lesson is called, exponential functions. We're going to look at some vocabulary terms: exponential function, exponential growth function, exponential decay function, and an asymptote. And I would like to point out to you the difference between the growth function and the decay function. If you look at the values for the growth function, our b has to be greater than 1 and a has to be greater than 0. But if you look at the decay function, our value of b is in between 0 and 1. So if it's going to be a growth, it has to be greater than 1, and if it's going to show decay, it has to be greater than 0 but less than 1. Okay, so moving along. I'm sure you guys have explored exponential behaviors before. One thing I always like to look at is my family tree. This is my Grandpa Jonas. At one point it was just my Grandpa Jonas. Hold on a sec. Okay, so I got cut off. Sorry about that. But anyway, when I'm teaching this unit, I always like to begin by looking at my family tree. My Grandpa Jonas had 2 boys. Greg is my dad, some of you know him, bus driver Greg. And then Tony, which is my dad's brother. And then my dad had 2 girls, Deborah and Leah. So far, my sister has had a little girl named Phoebe, and I've had Eli and Miley. My Uncle Tony had a daughter named Candace and a daughter named Brandy. At this point, Candace has a daughter named Layla, daughter named Kirsten Wisman, as you guys may know, Elena, and Erica and Elena. And then my cousin Brandy, we're just going to assume that she has 2 babies. I don't know. At this point, she doesn't have any. But if you think about, look at how this has grown. In one generation, it was my grandpa. The next generation, he has 2 boys. Then each of those boys had 2 kids. And then if each of those kids had 2 kids, you can see how quickly things grow exponentially. And this is what happens with populations. So if they say that a population grows, let's just say it was by 1% each year, that doesn't sound like very much. But if it grows by 1% that year, then all of that new growth is having 1% more. You're going to have 1% more on top of that. And then 1% more on top of all of that the following year. And so it just gets bigger and bigger and bigger. And that's known as exponential growth.
Could you please come down to the office?
So with exponential behavior, how does that look, and then different? How would that look on a graph in comparison to linear? Think about that for a second. If something grows linear, we know that it grows at a constant rate and the graph is a straight line. But if something grows exponentially, it's growing at a much quicker rate. So let's fill in this table. You guys can just follow along. Let's fill in this table to kind of see what it looks like. So we're saying that x is equal to 0, and we've got the function f of x is equal to 2x. So if I plug in a 0, 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times this 3 makes 6. And 2 times this 4 makes 8. So this would be a linear model. But exponentially, see, our exponent is now the variable. 2 to the 0 power. Anything to the 0 power is always, I hope all of you said 1. 2 to the first power is 2. 2 to the second power, that means 2 squared. 2 times 2 is 4. 2 to the third power, that's 2 times 2 times 2, so that's 8. And 2 to the fourth power, that's 2 times 2 times 2 times 2, which is 16. Quickly, you can see that it's taking off and it's going to look a lot different. Okay, so we're going to move on to our next, looking at some exponential behavior. So an exponential function is a function in the form of y equals a times b raised to the x power, where the a can't be equal to 0, b has to be greater than 0, and b cannot equal 1. Obviously, if a or b was 0, then there wouldn't even be a function, because 0 is just 0. So that's why it has to be greater than 0. And the base is a constant, and the exponent is the variable. So remember our parts of the power. The base is this AB, and the exponent, that's the little number, is the variable. So if I have y equals 2 times 3 raised to the x power, my base is considered to be this 2 times 3, specifically the 3, and then the exponent is the x. Y equals 4 to the x. Well, my base is 4, my power or exponent is x. 1/2. Now, does this meet the criteria? We said that b has to be greater than 0. This does not meet the criteria of an exponential. Oh, yes, it does. It's greater than 0. I'm sorry, I'm thinking for growth and decay. So this would show, these two would show growth, but this one would show decay because it's between 0 and 1. These would show growth because they're greater than 1. We'll get more into that. I'm getting the cart a little ahead of the horse here. So this is what an exponential function looks like. A linear function, y equals x, looks like this, just a straight line that passes through the origin. The slope goes up 2 over 2, up 2 over 2, or up 1 over 1, however you want to look at it. Y equals 2 raised to the x power is an exponential function. It's no longer linear. It's growing at a much, much quicker rate. So with linear, you can see it's growing at a constant rate each time. But an exponential rate of change, there's a small amount of growth, then a little bit bigger, then a little bit bigger, then a little bit bigger, and it just keeps getting bigger and bigger and bigger each time. So let's look at an example here together. Identifying exponential behavior. Now, this is, I do believe, in your book. It is on page 490. If you would like to fill it in as we go along. So earthquakes, I find this very interesting. The Richter scale measures the energy that an earthquake releases and assigns a magnitude to it. These orders of magnitude can be approximated by comparing them to the explosive power of TNT. Determine whether the set of data displays exponential behavior. So looking at this, look at what's happening. It was 0.6, then it jumps up to 6, then it jumps to 60, then it jumps to 600. So as the order of the magnitude increases from 1 to 2, the amount of TNT that is approximately equal in magnitude increases from 0.6 tons to 6 tons. That's an increase of a factor of 10. Each time you can see you're multiplying by 10. So as the magnitude goes up by 1, the amount of tons of TNT goes up by a factor of 10. We're multiplying by 10. So since the change in the amount of TNT increases by the same factor, given an equal change in magnitude, the data set displays exponential behavior. Okay, so let's look at growth and decay. So in an exponential function, the independent variable is an exponent, and the function is defined as y equals a times b to the x, where a cannot be 0 and b must be greater than 0 and cannot be equal to 1. So let's look what happens here if our a gets bigger. And see, if b is just at 1 and a gets bigger, there's no change. It's just a line moving around, right? But if my a gets bigger and my b is greater than 1, it's growing. Look at that. It's getting steeper and steeper. The bigger the number, the steeper the graph gets. Let's look what happens if we change that a to an even bigger number. It's just moving. The a is moving the y-intercept. It's changing where the line crosses the y-axis. So that's interesting. When a is 3, p is crossing the y-axis at 3. When a is 2, it's crossing the y-axis at 2. When a is 1, it's crossing at 1. We could keep going all day with this. Okay, and let's look at what happens when b is greater than 1. My function is growing exponentially. But when b is less than 1, it's decreasing exponentially. It's going down instead of up. So when we're on this side, it's in the negative, or not negatives, but it's between 0 and 1, it is decreasing exponentially. But when it gets above 1, look at the change there, boom, from doom to doom, there it goes. Now it is growing exponentially. So that is important to take note of. When the value of b is greater than 1, it shows growth. When the value of b is between 0 and 1, it shows decay. Okay, and next, graphing exponential functions. So functions of the form f of x equals a times b raised to the x power, where once again a cannot be 0, or must be greater than 0, and b must be greater than 1. These are called exponential growth functions. Where b is greater than 1, it's an exponential growth function. When a is greater than 0 and b is somewhere in between 0 and 1, this is called an exponential decay function. And the graph of exponential functions have what's called an asymptote. An asymptote is the line that the graph is approaching. So, let's see here. If we go back to that previous example, let me show you where we were moving those along the x-axis. As you can see, this line goes down, 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 and it gets closer and closer to the x-axis. It looks like it's even on it, but it will never get below it. So that's what it's talking about with asymptotes. Okay, and then there's just some important things. I'm going to go through this really quickly, but for it to be growth, the value of b has to be greater than 1. For it to be decay, the value of b has to be sandwiched between 0 and 1. For my domain, for a growth function, the domain is all real numbers, and the range is all values of y greater than 0. For decay, same thing. All real numbers is my domain. My y values or my range is any number greater than 0. Okay, for exponential growth functions, there's only one y-intercept, no x-intercept. Same thing for decay functions. There's one y-intercept, no x-intercepts. And for exponential growth, as x is increasing, f of x is increasing. For a decay function, as x is increasing, f of x, or y, is approaching 0. And then last of all, this is what the graph looks like. An exponential function that's showing growth is going up, and one that's showing decay is going down. We're going to watch a brief little video. First, we're going to choose values of x. So -2, -1, 0, 1, 2, and 3. Then we're going to plug those in place of x and solve for y. Then we graph the ordered pairs. Draw a smooth curve to connect them, and you have just graphed an exponential function. Okay, and I think we're going to call it quits for today. If you would like to continue working through some of the examples in your book, there are 2 more examples in your workbook, and you can follow along with those. And then I'm going to assign you some practice problems that you will do through McGraw-Hill, and there will be a link underneath of this video. If you have any questions, feel free to email me, reach out to me, and I will be seeing you in our live chat on Thursday.